Okay, so let me formally introduce our speaker today. Good evening, everyone. Welcome to the 18th talk of this year's CASILab Saturday Lecture Series. CASILab, the Center for Advanced Studies and Innovation Laboratory, is dedicated to demonstration-based science education, research, and innovation. It serves as a platform for institutional, independent, and grassroots researchers to pursue innovative projects. This initiative was founded by my teachers, Dr. Tushar Kantide and Dr. Surajit Singh, who devoted their lives to advancing physics research in this region. Today's lecture continues our celebration of the International Year of Quantum Science and Technology. I'm truly honored to introduce today's distinguished speaker, Professor Buddhadev Bhattacharjee. He is currently a professor in the Department of Physics at Guwahati University, where he also served as the head of the department, and he is currently also a guest scientist at GSI Darmstadt, Germany, and an associate scientist at CERN Geneva. Professor Bhattacharjee completed his master's from Guwahati University and earned his PhD also from there, jointly with the Nuclear Science Center, New Delhi. He pursued postdoctoral research at GSI in Germany and at Banaras Hindu University. His research focuses on the properties of nuclear matter and under extreme conditions, particularly as formed in ultra-relativistic nuclear collisions. He is currently leading a major DST-sponsored project values more than 3 crore, has mentored several doctoral scholars, and has published extensively in leading national and international journals. Professor Bhattacharjee is the principal investigator of the Guwahati University group involved in 2 of the world's most prestigious experiments, the LHC ALICE experiment at CERN and the FAIR CMB experiment at GSI. He serves on the collaboration boards of both ALICE and CBM and was recently elected as the chairman of the ALICE Star India collaboration. Furthermore, he has significantly contributed to the regional scientific development, having served as the General Secretary of the Physics Academy of Northeast for 2 consecutive terms. Professor Bhattacharjee will intrigue us with a fundamental question today. Do quarks really carry baryon number? Let us warmly welcome Professor Bhattacharjee. Sir, the platform is yours.
Thank you, Dr. Nath. So, I'd also like to thank the organizer for giving me this opportunity. So, the plan of my talk would be, so what I would like to do, I would like to spend a few slides on our current heavy ion research activities first, and then I'll go to the topic of today's presentation. Here also, I will first introduce the genesis of the present work, and then I will try to take up the issue of the true baryon carrier. Now, I would like to take almost equal time for these 3 topics. And while doing so, I'll try my best to complete within an hour, within the stipulated time as given by the organizers. But in any case, I might take 5 to a maximum of 10 minutes more, as I have to present few slides on the very fundamental aspects of heavy ion collision, as I understand that uh, uh, many of my audience today may not be from the same field where I belong. So please bear me if I am late by 5 or 10 minutes maximum. Side. And the talk is LAC Alice of CERN, Switzerland. We have been currently running a project worth rupees 3.62 crores, and we have completed the last project uh, of rupees 2.45 crores. Both the projects were funded by our Department of Science and Technology. So we have signed MOU with Fair CBM management. So you can see that this is the signature of our register. This is myself, and these are the people from the Fair management. Also, we have signed an MOU with Alice. You can see this is our register. This is myself. This is sound director, and this is Paolo Giubilino, who was the Alice spokesperson. So this CBM MOU, you can see this is actually, initially it was signed in 2009. And recently it was renewed in the year 2002, sorry, 2022. And this was signed in 2013. So we are very much in the part of these two major collaborations of heavy ion collisions. So this is our first result of Alice data analysis that we do. So this is actually the result of run 2 data of lead collision at 5.02 TeV. I could see that the actual analyzer, my student Noor Hussain, is there in the audience today. So we did this analysis. Our task was actually all through. We have been analyzing, we have been identifying rather the light flavored particles, mainly ions, kaons, and protons. We generally use TPC and TOF detector. You know that ALICE is a very large detector. So these are the works that are being done by a cluster of institutes from ALICE collaboration. This result is being conducted by Guwahati University in association with INFN Bari, then Mexico City ICL, Bologna University, Turin University, and Lund University of Sweden. So these 6 people or 6 institute has analyzed this this data and presented, published the result. Now, as I said, ALICE is a very large detector, and it is a collection of detectors. So you can imagine that how big the detector is. This is the height of a person. You can compare the detector height with the height of a person. So this is almost, say, 7 to 8 story building. So it's not possible for one person to do all the data analysis. So what is done, the management, they make a group and assign some tasks, and we do this analysis. So this is the TPC. TPC is believed to be the heart of the ALICE detector. And you can see that this number 5 is that golden color is our time of flight detector. So these results was published in Physical Debussy. Then you can see that this is the complexity of an event. This is one event of very gold collision. LSC events are even more complicated because the energy is high, the system is larger. So you can imagine this is one event. You have to follow each and every track and then find the particle. You cannot see this actually. This is simulated. Uh, uh, you have only the data that are stored in the server. So without seeing anything, you have to find out the particle out of this mass, the particles which are of your interest, and then you subsequently do your physics analysis. So that is what actually we are doing all through. So this is another work done by my another student. The earlier one is I did with Noor Hussain, one of my Sharma, who has already obtained his doctoral degree. So this is again the run-to data of proton-proton collision at 13 TeV. That was the highest energy available at that time. Now we are taking data for run 3, and this is little higher in energy. This is 13.6. So this was again, this analysis was conducted by Gothenburg University, the University of Copenhagen, Turin University, University of Greece, and Lund University. So here we did, our task was to identify pi kp with a time of flight detector. So we did, and the other people have done with other detector. Then we compile all the results together and then publish it. This was published in EPJC in 2020. So then we are also assigned with some responsibility time to time, that is what is called the institutional review committee. So in Alice, if you are going to publish a paper, we cannot communicate this paper directly to the journal. You have to pass through a number of stages, and in every stage, your results will be cross-checked, examined, scrutinized, evaluated, and people may suggest the new, analysis. They may ask for new plots, and you have to satisfy them, their queries, and then only you can move to the next level of scrutiny or evaluation, and then finally the will go to the journal. So this is a very lengthy and meticulous process of publication. So what is one such stage is institutional review committee. What is done when a paper is written? So this paper is then communicated to a few institute who, depending on their expertise, and then this IRC people will suggest modification changes, may ask for new data, may ask for new plots, and they may also even stop its further proceedings. So this is a very important and crucial step in the entire process. So we have been assigned occasionally this responsibility. I have cited a few only here. So this is here, you can see that Guwahati University, along with the St. Petersburg University of Russia, then Wayne State University of Michigan, CERN. And this paper was published in Nature. Then similarly, we have done this IRC responsibility, and that was published in Journal of High Energy Physics, and then of course EPJC, and so on. So this is another work that we do side by side along with our data analysis and physics analysis work of ALICE and CBM. So this is mainly what I am showing is ALICE, because CBM is yet to take its data. So our students are very much engaged. They are going CERN almost twice in a year. They participate in CERN's activities. They participate in ALICE experiment, and also do physics analysis and other works at CERN when they visit. So this is, as I said, the Noor Hussain, this is Pranjal Sharma, this is Bonajit Burman, and this is Tanmay Sharma. They are now my current student, Bonajit and Tanmay. So we are very much engaged. We are involved with all ALICE activities, and the PID, that is the ion, kaons, and protons that we have been actually identifying. We are identifying the entire collaboration, not for our work only. So based on this, our identified light flavored particles, the other analyzer will do. Like you know that lambda is a unstable particle. It decays into protons and pion. So if anybody who is working on lambda, he has to take our pi kp, and then similarly for other hyperons. So whatever we are doing for the entire ALICE collaboration, not for the Guwahati University group only. So these are some facilities we have developed here at Guwahati University. This is one high performance computing cluster we developed with ALICE Fund. And then this is something we have developed on a detector R&D related lab. We are looking forward to do more activities using these facilities in coming days, when maybe we will be a part of a focal detector of upcoming ALICE experiment. So this is, you must be knowing that the Ford experiment of CERN has got the breakthrough prize of 2025, And Alice is also one of the experiment which has got this breakthrough prize. And in the list of the Alice experimenter, the 5 members from GU's names were there in the list of the breakthrough prize owners. So these are the people whose names are there in the list. So with this, I have made some a little bit of introduction of our activities. So with this, let me come to my today's topic. So as I said, that many may not be from the same field. So let me introduce some basic ideas of high energy physics. So this what we call the elementary particle. They are not truly elementary, but when these were discovered, it was believed that they are the ultimate building blocks. So they were said elementary particles. Now we know that they are not fundamental particles. So let's call them elementary with the same status. So these are all elementary particles. I mean, they can be divided into 2 categories. One is leptons, and the other group is called hadrons. So leptons are those particles which take part in electromagnetic and weak interaction. So electrons, positons, muons, and neutrinos are leptons. And hadrons, they take part in all 3 interactions of the standard model, that is electromagnetic, weak, and strong interactions. So these hadrons are again divided into 2 classes, that is what is called mesons and baryons. So mesons are made up of 1 quark and 1 antiquark. Baryons are made up of 3 quarks. So this our prime interest is with baryons. So as you know, that baryons are again divided into nucleons and hyperons. Nucleons are basically protons and neutrons. These are the elementary particles which are found inside the nucleus. And hyperons are actually, they are not available in the normal phase space. They are produced in exotic collisions like relativistic nuclear collisions. So one peculiar property of such elementary particle is that any heavier particle will decay into the lighter particle. For example, if you take this neutron is heavier than proton, so it decays into proton, electron, and neutrino. This is a well-known beta decay interaction. So through beta decay, a neutron decays into proton. Similarly, a lambda hyperons decay into proton, lambda being heavier, so it decays into lighter mass particle, proton. Pion is heavier, it decays into muon, muon again decays into electron, and so on. So, the heavier elementary particle decays into the lighter elementary particle, with one exception. And the exception is with proton. Now, a free proton never decays to a lighter particle. Its lifetime is of the order of 10 to the power 39 years, which is more than the lifetime of our universe. So what we find that this proton, it does not decay into pions or kaons or say electrons. So to explain or to give a justification for this observation that this unusual stability of the proton, we introduce a new quantum number, what is called Baryon quantum number, and a corresponding conservation law, what is called the Baryon number conservation law. And this law states that for a closed system, the Baryon number before and after interaction is same. No new baryons can be produced. If they are produced at all, the equal number of antibaryons should have to be produced so that the total number remains constant. Now, if you look at this decays, the neutron is a baryon, so its baryon number is 1. Proton is a baryon number is 1. And these are non-baryons, so 0, 0. So left side 1, right side 1. Here also this is baryon 1. This is baryon 1. Ion is 0. It's not baryon, it's meson. So 1, 1. These are mesons, and say muons is not a baryon, so 0, 0. So any nuclear interactions or all these strong and electromagnetic weak interaction, the baryon number is conserved. So this is the rules that we have to remember for our further understanding of the today's talk. Now, what is a relativistic heavy-ion collision? You can see that this is the picture. Since the two nuclei are moving almost to the speed of light, we will not see the nucleus as a spherical structure. They will suffer Lorentz contraction and they will appear as pancake. So nucleons, these two nuclei are nothing but the cloud of protons and neutrons. They will come and collide. This collision is a statistical process. They can collide head-on and they can collide, say, at a grazing angles. Head-on collisions are called central collision. Grazing angle collisions are peripheral collision. And in between, we call semi-central collision. So you can see this is one nucleus, another nucleus is coming. So this brownish area is the actual overlapping region where the actual reaction is taking place. There, hard scattering of nucleon, and also the quark scattering will take place. So these are called actually participant, and the portion which is outside, they are called spectator. So, I mean, this rigorous collision will take place in the participant region, and spectator will just basically see that what is happening here. But it's something like, the situation is something like a cricket stadium. The spectators are moving in the gallery. The match is going on and it is being played by, say, 20. So though the spectators are not participating in the game, but they are not totally out of influence of the game. So they are also getting influenced by the ups and downs of what is happening in the participant area. So now what happens is that since this is coming from this direction, if I go back and if I can show you again, so since it is coming, so one is coming, say, from the left direction, another is coming. So what happened? This spectator part will will move will move along this direction, and this will move along this direction, and they will finally disintegrate into, say, they might disintegrate into nucleons, that is protons and neutrons, or even their constituent quarks. So this is important for us. Our whole entire study is actually based on this. What is actually the effect of spectator on this entire collision dynamics? That is what we are actually interested in. So, and everything will happen. So we started with a cloud of nucleons, and we end up again with nucleons only, or we started electrons, we end up with electrons. We want to many things might happen. So we cannot measure them with this this time. So what the entire analysis done in a very way indirectly. So I won't go to details of those today. So one important parameter for today's discussion is called rapidity and rapidity distribution. So let me define this quantity to my audience who are not used to it, say, high energy heavy collision. So you remember, we all know the famous Rutherford scattering experiment. So alpha particle is coming from the alpha source and falling on the gold foil, and it will be scattered in different directions. So some might scatter at a very large angle. So what he did is he measured the different scattering angle, and then he came to the conclusion that at the center of the nucleus, or at the center of the atom, there's something called nucleus. Now, this angle is not a very good parameter for relativistic heavy ion collision because it is not Lorentz invariant. So we are looking for a parameter which is Lorentz invariant and also which can provide more information than the only direction. So what we do, we define a parameter called rapidity. It is defined as, say, half log E, that is energy of the particle, plus Pz, that is the z component of the momentum of the particle, into C, then E minus Pz. Now, you see, this is one particle is coming, this is another particle is coming, and this is the perpendicular distance between the two colliding nuclei. So you can imagine, you can draw a plane with the direction of the incident nucleus, say z axis, and also the another axis being that is called impact parameter, or the perpendicular distance between the two nuclei. Now, if B is 0, we call it head-on collision. If B is maximum, we call it peripheral collision. Now, You can also imagine a plane which is transverse to this reaction plane. So this is called transverse plane. So if a particle is emitted along this transverse plane, in that case, its pz will be 0. So these two terms will be 0, and log of E by E is equal to log of 1. Log of 1 is equal to 0, so I will be 0. So any particle which is moving along the transverse direction will have rapidity 0. And any particle which is moving along the beam direction will have rapidity infinity. So, and the rest of the particle will have rapidity between 0 to a large value. So we can get from the rapidity information, we can get the direction of emission of the particle with respect to the transverse plane. And now, if the particle is emitted along the transverse direction, we understand that its pz is 0. So it will be moving with the highest, so highest transverse momentum. So we not only get the information about the direction of the emission of the particle, we also know about the velocity or the momentum of the particle. So that is the advantage of, and it is Lorentz invariant. So we take rapidity over polar angle theta of the each particle. Now you have seen the event. In one event, say 2,000 particles are coming, and we study say 1 billion data, 1 billion events. So 1 billion into 1,500 number of particles we study, and then we draw this rapidity distribution. So this is called the rapidity distribution of a particular particle. If say in our case we are interested in pion, kaon, and proton, so we draw this vector, and this is what is the full width and half maximum, or you can take RMS value. This is the width of the rapidity distribution. Now, this is an important parameter from the point of view that this is a measure of scattering that a particle suffers while it is coming out from the fireball. So, sigma gives me a measure of the scattering of each particle. So this is important from that point of view. Now, when we started our work long back in 2008 or 2009, we came across a paper published by this Na49 groups. So this is these are the result of three collaboration result. The one is E895, E802, and Na49. Na49 is the same, actually, Alice collaboration. Earlier, it was known as Na49 to Alice. So they published a paper on the measurement of rapidity width, and they observed that for a particular particle, you can see that these circles are for pions, and these are for kaons and phi mesons like this. So what they observed that as the energy increases, the rapidity width increases. And more interestingly, what they observed that at a particular energy, the rapidity width is maximum for the lighter particle and it is minimum for the heavier particle. So based on that, they proposed a universal mass scaling, and they have drawn it here. So you can see this is the pi, this open circle is pi, and this other side you can see their particles are on the top, pi1, k1, this is k1, and so on. So they observe a mass scaling. As the mass increases, the width decreases. So Na49 proposed the universal mass scaling. What they miss is that they has ignored this difference between K plus and K minus. This this is K plus, the solid circle is K plus, and this is K minus. Now they have a reason to do. They believe that since the error bar is touching this straight line, so this difference could be due to the error. But if you look carefully, as the energy increases, this difference is more than the error bar. So somehow they missed. I mean, this point has missed their attention, and there is another point which I will narrate in my coming slide for a better understanding. So what we wanted to do is that we have seen that okay, these people have done the experimental result, they have published their experimental result, but they have not done any comparison with the model calculation. So we thought that we will do this model calculation. We started with one of my first student with this on this collaboration business. So uh, we took a model which is very popular and very successful, what is called URQMD model of heavy ion collision, and we compared this data, this experimental data, with our model gener. This solid line is our model generated plot, and this squares and circles are actually experimental data of all those collaborations. So you just trust me that we find, because there are some disagreement, something, these are because of only nothing. If you do the proper things, it will come. That results more or less agree. You can see pi1 agrees, k1 agrees. If you take the contribution of lambda from sigma naught, then lambda also agrees. This is lambda plus sigma is on the I mean higher plot. So this agrees well with our black solid line. So they are agreeing. And here, since the error bar is very large, we believe that this is also agreeing. So now, so what we do, we measured this repetitive width and we then plotted this mesons and baryons. So we plotted mesons in a separate plot, baryons in a separate plot. We observe the same thing. That is, this pion, you can see that this width increases as the energy increases. Y beam is basically energy. It's a matter of energy of the incident. So then pion, below pion is K1 and then pi meson. So there is a mass ordering of mesons. There is a mass ordering of baryons. Lambda is the lightest baryon, omega is the heaviest baryon, so it is below. Now, when we mixed up these two, mesons and baryons, then a marvelous things happened, which is beyond our expectation. What we could see that a flip-flop occurs at mesons and at phi mesons and lambda baryons. So phi has lighter mass than lambda. You can see from this table, phi mass is 1019, lambda mass is 1115. So lambda is heavier. So it should have more width. But if you see in this plot, you can see that since it is heavier, it should have less width. It has more width than the phi. So is this flip-flop is occurring. So initially we thought that we might be we might have written the code wrong, or our data that we have generated might have some problem. So we rewritten our code. We have generated again millions of events again, and then we completely reanalyzed the data, and we come across the same result. Then we thought that this must be something real that is happening. So you can see that something like mass ordering violation is taking place. So you can see from this plot better. If you plot again mass, you can see these are the three mesons, these are the baryons, and there is a jump occurring at lambda. Now let me go to the earlier point that I skipped. That what is the second point? If you look at this second point, you find that here, this NF49 and other column, what they did is they did not consider lambda. They rather considered anti-lambda. And that is the crack of the entire analysis. When I asked actually the spokesperson of NF49 at that time, or rather physics coordinator of that time was Volker Freise, who happens to be one of my friend. He came Guwahati University thrice. So, so I asked him, what is the, I mean, why did you not consider lambda, and why did you consider anti-lambda instead of lambda? Then he said that because we thought that lambda decays and lambda contributes, lambda has got contribution from sigma naught, and sigma naught contribution will contaminate the data. So we thought that since lambda and anti-lambda are same mass, so there is no harm considering anti-lambda over lambda. So they did it like that. And there they miss the entire story. So, so when we, so what to do next? So we thought that, okay, let's see how their experimental lambda is behaving. So I asked my student that you go and then search the journals and see if we can get the lambda distribution anywhere in the published result. So then he came up and he said that there are at least 2, 3 results of lambda is available at 2, 3 different energies. We can take those width and we can put it, and we put it, and we surprisingly find that in different experimental result, if we collect and compile, we see the same jump. That's what they missed. So there is a clear-cut violation of the mass scaling as claimed by the Na49 collaboration, that is Sun collaboration. So we thought that we are done. We have now proved that the mass ordering is violated. So we communicated the result with the journal, and unfortunately the journal denied to publish because they said that okay, your work is correct, you have done right kind of observation, but since it is not the fastest data, so you must have to give an explanation for such observation. You have not given provided any observation. So you understand that without giving proper explanation for such observation, we cannot get a good publication. So we were looking for this. What could be the reason for that? So we understand that as certain people claim that width is it's a kinematic issue. That is it's a trivial things. If you take a small mass and throw it, it will go a larger distance. If you take a heavier mass and throw it, it will go a smaller distance. That is something kinematic thing. There is nothing dynamic underlying physics. So now we realize that this is not merely kinematic. There is something else there. Now we have to find what is else. So we challenged one result, and we started thinking about what could be this something else. So we looked into what the difference between lambda and lambda. So what we found is that lambda is of 3 quarks, anti-lambda is made of anti-quarks. And interestingly, out of these 3 quarks, 2 quarks are actually leading quarks. Leading quarks means these are the quarks which can be found in the incoming nuclei. That is, our nuclei is made up of protons and neutrons. Proton is nothing but 2 up quark, 1 down quark, and a neutron is nothing but 1 up quark, 2 down quark. So this lambda might get the contribution from the leading nuclear. So if you remember, I said that this the spectator part will go in the forward direction, and they will populate the fragmentation region. That is, beam direction. So what we understood is that from when this protons and neutrons of the incoming nucleus will dissolve, so they will make up and down quark available at the larger rapidity side. And it is possible that those up and down quark will one as and it will form lambda. But this cannot be possible for anti-lambda to form at larger rapidity. So we understand now very clearly that this is the reason for the production of lambda at larger rapidity, which is ultimately given the width of lambda larger than the anti-lambda. This is one region, and another region is associated product. This is something also related to the protons and neutrons. So we understand that lambda width is larger because they are produced. Some lambdas are also produced due to the contribution from the spectator of the incoming nuclei, and that is why the width has increased for lambda and the anti-lambda will be mostly produced in the central rapidity region. It is at y is equal to 0 and around that space. So once we got this explanation, we communicated this paper to WC, and that was published without being straightforward publication. So we got now we okay. We have seen it at lower energy, that is this and AGS energy. Or what is happening in higher energy, at SPS and REAK and LAC? Is this down? We also did one interesting thing is that we propose separate mass scaling for mesons and baryons. We proposed that universal mass scaling is violated. We did not take that term. I got a request from Volker that don't be so harsh on us. Don't say that mass ordering is totally violated. It is still followed if you consider measures variance in different parts. So we uttered this term that separates mass scaling for measures and variance. And we proposed it for the first time for any heavy ion collision related data. I am saying it with credibility. This is 2014. I mean, you can search any journal and find if there is this term that separate mass scaling. Now, this separate mass scaling is now being observed in many other parameters, and people are using this term of separate mass scaling. But has been evolved from the university. So then we try to see whether this is happening in all other data, and we can see that this is also happening at CLR. So we again communicated this result to another. You can see that from the lowest energy available at CERN superproton synchrotron to those at BNL, relativistic heavy ion collider, and then at so we covered the whole energy from CIS to LHC, and we see that this jump is a general property of the relativity. So that is what our actually the basis of this our current analysis on proton-proton collision, and this the do quark really carry the Baryon number. So at present we are studying, as I said, that we are studying the Ramsey collision, and also at the same time we are trying to understand the dynamics from our phenomenological study. So as you know, but one thing is important here is that at LHC analysis, these protons are not 2-point like. Protons is not considered as a structure of 3 valence quarks and few gluons, and these are collide with each other at head-on. So what it is believed that at this energy, the proton itself is a very composite structure made up of valence quarks, then lots of C quarks, and many. So it is a composite structure. And since it is a composite structure, it is possible that the collision could be again central, and peripheral. That is, there could be something which is beyond the overlapping region. That is, again, there could be again something which is spectator. Sorry. Now the difference is in heavy ion collision, the spectator is made up of protons and neutrons. That is nucleus. Now in PP collision, the spectator is made up of the partons, that is quarks and gluons. So we wanted to know, just like in case of early heavy ion collision, the spectator nucleons play a role in lambda production. Do this parton also play in the production of lambda? So we started our phenomenological work. This PP collision is centrality dependent collision. And unlike, say, heavy ion collision, here the spectator is pattern. And the motivation is to find the role of the spectator pattern on lambda. Now, we know that in QCD, the valence quarks is believed to be the carrier of electrical color charges, flavor, isospin, and Baryon number. So this is a standard textbook that electric with the quark of the constitutive baryon and all other parameters do carried by quark itself. Now there is a paper published in 2000 that is garbage study this reaction. Ion is interacting with proton to give you omega ions. Now if you look at they are made of this. So proton are 2 quark, 1 quark, and omega is 3 s quark. Here the baryon number is this, baryon number 1, rest are 0. So baryon number is conserved, left side is 1, right side is 1. So this is, is an observable interaction of strong interaction. So there is no issue. the problem there, they pointed out that if you look at omega, omega does not contain any of the quarks of proton. Constituent is up quark and down quark. Then how is baryon number? Who has carried baryon number 1 to omega from this side to that side? That was the issue. So people now started realizing that assigning baryon number to a particular pattern is not a straightforward issue. It is much more complicated one, as and beyond our comprehension, at least at this moment. So, is it the other pattern or only string junction which could be carrying this baryon number? Now, what is a string junction? It is like the whole of a Mercedes. It is a string, and inside baryon, this 3 quarks will be connected at the 3 corners of this string. So this is what is called a string. So many people started thinking that it is possible that the baryon number is at the middle of this junction. Now there are two groups. At one is BNL, Brookhaven National Level in New York. That is Zavitri Kharji, and there is Peter's of both group that from the first principle that in nuclear collision it is not necessary that the baryon numbers and charge should move together. That is, quark and quark should carry number. So they that string junction and quark not necessarily has to move together. It is possible that it will get isolated from the string junction, and it is possible that the quark and string junction will move independently. In that case, if the string junction is at the middle of the point, we realize that the baryon number by the string junction and the charge will be carried by the quarks. So in that case, one must anticipate that the charge and the baryon number will move independently. And there are experimental results. I have shown it here. They observed that there is the electric charge and the baryon numbers are not moving together. There is definite signals that they are moving isolatedly, they are moving separately. So all these baryon will be carried by. So with this idea, so they have developed. They have been using one basic model of proton collision study is called PITIA. And then they are doing some theoretical. Their approach is completely fundamental. Is that it is curves and string junctions move separately, giving the motion of charge and baryon number. And trying to explain various observed experimental results. They are not. I mean, we should not say that all their is were. They are getting success, but not models. I mean, could not explain all the results. And we entered at this juncture in the whole analysis. So what is the model? So this is that people are believing, and this was the earlier model that 3 the bonds are interacting with every one of them. So that structure in the earlier model, here it is believed that these gluons are in a Y-shaped structure. So that is the fundamental difference. Now we have seen in the literature that there are results of lambda and lambda measurement ratio of lambda measurement for both LIS and LSCB experiment. Now, LSCB, LSCB is an experiment that was designed to find the explanation for matter-antimatter imbalance. That is why our universe is matter-dominant. Where all those antimatter has gone? What is the physics behind that? So the LSCB experiment is to give answer to all these queries. So this is very important experiment of LSC. So we have seen that they have also measured. LSCB is basically a large acceptance detector. They have a larger in the this LSCB is a detector which detects particles which are emitted at the mid rapidity. At and around mid rapidity, its acceptance is 0.8, from minus 0.8 to plus 0.8, and this is from say 2.45 or something like this. So this is at larger rapidity, LSC. So this we can see that these are the results. Now they have many models. LSCB results are, I mean, say 15 years old from now, and their result, they wanted to give explanation for existence, and they failed. All those models, none of this model could successfully both LS and LSCB result. Mostly the LSCB result. This result is okay, fine. So as you result, most of the model can do, but when they come to the LSCB result, all this model fails to explain. So what our intention was, can we find a model that can explain both LSCB and LSCB result? What we do, we started with a default model, which is being used traditionally. So in this model, so we have generated for say 7 TB PP result. We have chosen 7 TB because this is the highest energy experimental result is available at 7 TB and 0.9 TB. So we started with 7 TB. At that time, the run-to data was not available. Run-to experiment was not done at LSC. That is the story of before run-to data taking. So we do not have the 13 TB data or result. So we started with this. So when we draw the rapidity distribution of lambda and anti-lambda with the Pythia monas over full rapidity speed, so we find a very interesting result. We find there exist two humps of lambda. That is, more lambda are produced, just like we have seen in heavier collision. We can see that more lambda are produced at highest rapidity. But anti-lambda, there is no such humps. So we understand that something must be contributing here. So in the Pythia monas model, what is believed that a baryon is composed of 3 quarks. So so proton-proton collision is the collision between this quark and another proton will be here. So these two quarks, one from this and another from this, they will interact, and these two quarks, they will go as if that they will form a structure called diquark. So this diquark will now populate this fragmentation region. Just like earlier the protons and neutrons populated the fragmentation region, here this diquark will populate the fragmentation region. And it is possible that this diquark will capture another S quark to produce lambda here. And that we have seen a lambda hump. But since there is no antiquark here, so antiquark cannot be produced at this larger rapidity. So there is no bump here. So but the problem is this Pythia monas can explain. Pythia monas can explain the observed result at LS energy, but it cannot explain the LSC, which is around this rapidity, 2 to 4 region. This region it cannot explain. Now, what is the reason? See, you can see this is the Pythia result. It can explain this LS result. It is far from the LACB result. So if you take the ratio, you can clearly see that there is a large deviation, more than say 40%. So we have to explore with other models. So what we do? Well, so I mean, why? What is this? What is the reason for this difference? Here we understand that this lambdas are produced mostly from pair production. Equal numbers of particles and antiparticles are produced. So equal numbers of lambda and anti-lambda are produced. So the ratio is close to 1. This is, I mean, expected. But why more lambdas are produced here? So this model cannot. What we do is, you can see this. These are other parameters. Forget about this. The point, the PTR default cannot explain. The default means the model cannot explain the observed result. So now, in the meantime, the PTR model has developed quite a bit, and they have now introduced another model called string junction model. That is the one which we have been discussed. This is the that the blue one has got a topological structure, white structure. So this is so with this the Peter and his group, Peter are responsible for development. They this failed. They because of that fragmentation region. Since we have the experience of working with heavy ion data earlier, where we have seen that the fragmentation region contributes significantly in lambda production, in the code we make some minor changes, and we take the contribution of the fragmentation region in the production. So that is FR1, that is fragmentation region 1. And with this FR1, we can see that the nicely described both Alice and LACB. So we are done. So we understand that this model is successfully described the entire result of anti-lambda to lambda ratio, that is matter and antimatter asymmetry, both at Alice and LACB. Now, I mean, what is the reason for that? The reason, as we said, that you can see that here the proton-proton collision is believed to be the collision of these two quarks. They will suffer hard scattering, I mean rigorous scattering, and from this rigorous scattering, large number of hundreds of particles will come out, and these two, that is with this structure, this Y-shaped structure, with these two quarks at its end, and this side open without having any quark, because this has gone to the collision, it will no longer exist. So this will move in the fragmentation region, and after going to the fragmentation region, this two quark will get separated from the string junction and will become a logical object. So this liberated quarks will move independently, and this Y-shaped string will move separately. And because of the appropriate structure of the strong interaction field, this gluon will now feel an attraction towards the collision vertex. So it will move towards the central rapidity region. Since now the work in the earlier result, because it becomes it cannot move a very large distance from region. But since it is a string structure, it can migrate over a large region. So from 7 to 8, where there is a hump, it will be migrating to the 2 and 4 region. And when this string will migrate here, and while it will reach to the LACB region, it will immediately, or this 2 to 4 region, it will capture the 3 quarks, and this 3 quark might be UDNS, and it will produce. So in addition to pair production, lambda and anti-lambda, some additional lambda will be produced here due to the migration of this string. That is the anti-lambda to lambda ratio less than 1. So this is how we explain the LACB result. Then we thought that, okay, I mean, this all other results also we find that they are agreeing well. Then the PTR